In this video, I'm going to show you the complete guide to the design of 2-way slabs on Etabs. The condition given is shown: FC prime 5 ksi, Fy 60 ksi, slab thickness is given as 10 inches, floor height is 10 feet, it's a ground plus 2 stories building. The periphery beams are 10 inch by 12 inch, columns are 12 inch by 36 inch. Wall is 12 inch thick. The framing type is intermediate moment resisting frame or IMRF. The center to center span is 20 feet. The occupancy type is residential. Super dead load is 36 pounds per square feet. We have to use UPC 97 for live load and ACI 31808 for design and detailing of the slab. We have to design the first floor slab of the given condition. First, we have to check for two-way. Slab should be supported on 4 sides by beam and the longer to shorter span is less than 1. Hence the slab is two-way. So now starting with the new model. We need to define the grids according to the situation we were given. We need to go for 6 lines in Y direction and 4 in X. The center to center span was 20 feet. Number of stories is 2. Typical story height 10 feet. For ground floor height 10 feet. So now we are done with defining the grids for the condition given. Press OK. After defining the grids, let's first close the 3D view. We have to define the material properties. Add new material for concrete. We go for 5 ksi or 5000 psi. Check if the property is according to 5000 psi. Now add the steel bar grade 60 psi. Okay. Let's name it as G60 or deformed G60 for identification. Now we need to define the section properties for frame, that is beam and columns. The beam cross section to given was 10 inch by 12 inch. The property modifiers should be given according to ACI code. Torsion constant as 0.001 so that the beam is torsionally flexible. According to ACI code, it is 0.35 for moment in both the directions. That is about 3 axis and axis 2. Okay. So now modify show rebar. Click on beam and select the rebar so that Etabs will give you area of steel according to that grade of steel. Select the material for the beam, concrete. Now we have to add the columns cross section. Width is 12. Now adding the property modifiers for columns using ACI code, incorporating the crack moment of inertia that makes it 70% of the gross moment of inertia in both the directions, so that it reduces the column's capacity, incorporating the actual condition if cracks occur. For more accuracy, you may go for actual cracking moment of inertia and effective moment of inertia. So now once done, go for press OK. Now we need to define the section property for walls. The wall should be of 12 inches, or you may name it as W12. Select the concrete grade that was 5 ksi or 5000 psi. The property modifiers according to ACI code for walls is 0.7. We are assuming the wall is uncracked. You may delete the extra unwanted properties. Now defining the slab properties. That was given as 10 inches. The material property as 5000 psi. Now in order to understand the difference between shell thin and membrane, we need to go to the previous video whose link is given in the description of this video. You may also subscribe for complete Etabs tutorial. Now we will continue here with shell thin, assuming that you have watched the previous video. For slab, we have to place the crack moment of inertia as 0.25 for bending. Now we will model the structure. Start with drawing the columns. It is important that you note that if any node is missed, then you need to carefully place the column in the right position. A wrong position may lead to wrong result interpretation or computation. Modeling the shear wall. Now we will draw the slab, or just go for simple option. Draw quick floor on single click. Oh, actually I selected the wrong property. So I will press Ctrl+Z for undo and select the right property as slab for 10 inch and draw those slabs. Now we need to draw the beams that which we previously defined. The beams must be properly joined at the column nodes. Otherwise, a cantilever effect may occur, causing over-reinforced or abnormal behavior of the beam. It is also important that the slab forms a connection with the beams so that the load will transfer from slab to beams and then beams to columns. Make sure that the transfer path is complete. For cantilever part, we need the dimension of the cantilever part. So I am using AutoCAD here. The drawing is already prepared in AutoCAD, which we will label later. Enter the distance command so that we get the distance of the cantilever part. We are getting here as 2400 millimeter or simply 2.4 meter. So we can see, since we are working in FPS system, so we will convert the dimension into FPS. 2.4 multiplied by 3.281 gives the dimension in feet. It makes 7.9 feet approximately. So first, for modeling the cantilever part, we will draw a non-property beam and then later on delete it. Let's give the offset. The offset is in inches. So we need to convert 7.9. Actually, it was 7.9 multiplied by 12 inches. So it gives us 94 or 95 inches. Now we are ready to draw the cantilever slab using the help of non-beam. Once the slab is drawn, you may delete the non-beam. Now we have to apply the load on the slab. Or first we will mesh the slab. The span is 20 feet. The slab meshing shall be done in at least 3 feet, so which gives us 6.6. So we will round it up to 7 by 7 areas. For meshing videos, you may click on the link in description to know the actual logic behind meshing and how to auto or manually mesh the slab and why we do meshing. And various techniques of meshing are discussed in the video in link in description. The meshing shall be continuous. It is important, as I am assuming that you have watched the previous video whose link is given in description for meshing. Now divide in, since it was 7.9 feet, divided by 3, 2.4 meter multiplied by 3.281 gives us 7.87 feet. So the matching shall be done in maximum size of 3 feet. Dividing it gives us something like 2 times meshing area. So we divide it in round up figure as 3 meshing area. As finer the meshing, more accurate will be the results. Now we need to select all of the slab members. First of all, we will mesh the wall in the exact number as we mesh the slab, so that load transfer path is not disturbed and the meshing is continuous from slab to the wall, or you can say the meshing lines should be continuous from wall to slab. The wall was 20 feet, so we need to divide the wall into 3 feet, gives us 6.67 areas, or you can round up as we rounded up in slab part as 7 areas. The height was 10 feet, so we divide by 3, gives us 4 areas, or you can simply take 3 areas. Now these parts are matched. Verifying the other wall is matched too. Okay, so both are matched. Now we will edit the story data and quick add another story, since it is a 3-story structure, ground plus 3, ground plus 2, ground story or plinth level where there is no slab, or slab on grade, which usually doesn't require reinforcement in small projects. First floor slab, which is reinforced concrete, and the second floor slab. In this video, we are limited to design first floor slab. Check the floor heights, then press OK. We go to first floor elevation. Select all the slabs. Or first go to elevation. Assign pier labels to the walls. Pier label assigning is important so that the results of a particular wall segment is given as a joint element, which I will later discuss in the shear wall designing part. For now, you have to understand that each shear wall will get a different pier name, and the reason for that in detail will be discussed in the next video for shear wall design. So now we have assigned the pier labels. Now define the load patterns. Live load and dead load are already defined. We will now define as finishes or super dead load. The type is super dead. Self-rate multiplier 0. Add the load. Press OK. Select all the slab and now assign the loads. The dead load is already assigned due to the self weight. First of all, assign the live loads due to residential occupancy using UPC 97, that is 40 PSF. Click on replace existing loads if you don't want to add it in the existing loads. Now we select the previous selected member, that was slab, and add in finishes, which was given as 36 PSF. Click on apply. Right click on the slab to verify the load pattern is assigned or not. We may zoom out for a complete view. Press escape to deselect an element. Now we are done with assigning the loads to the slab which were given to us. It is not important to assign earthquake loads when we are designing the slab. First you need to select the design code. Design code for concrete frame I have selected right now. Now we need to select the design code for slab and shear wall. We go to the design menu and go to concrete slab design and click on view revise preferences. Select ACI 31808. Click on OK. Click on frame section, that is beam and columns. Select them all. Click on view revise overrides and change it to SOE intermediate since we are designing IMRF frame. Now clear the selection by simply pressing escape or CLR in the left bottom. Go to load combinations and add default combinations which will be added according to the design code you selected for concrete frame, shear wall and slab. You may check the load combinations you selected. You can also modify them when converting into user defined. Select design combinations. For frame they were already selected. For shear wall already selected, and for slab already selected. The selection was done by Etabs as default. Now you need to define a long-term deflection case for the slab so that we can apply the deflection limit for the slab on it. Take the dead loads as 3 times. Take the live loads and MAP loads as 1.5 times since the dead loads are sustained loads. Finishes is also category of dead load. Click on OK. Now we will have to draw the strips for this DDM method. Since Etabs work on the DDM method, you may also design an equivalent frame method. For that, zoom the slab and click on draw design strips. Strip drawing rules on Etabs or anywhere you use DDM are as follows. The column strip width is quarter of the shorter span in any direction. Here the spans are both same in the different directions. So the strip width is 20 feet divided by 4, that make it 5 feet or 60 inches per span. 60 inches on left and 60 inches on right, and the remaining portion will be middle strip. So now give the input to the Etabs. Strip layer A is written because we are interested in the reinforcement for longitudinal direction right now. For transverse direction reinforcement, you may go for strip layer B, which I will discuss here in the further part of this video after I am done with drawing the strip layer A. You may click on show width so that you can view the strip widths. Draw the strip widths from the top to bottom. Now draw the column strip near the columns and the middle strip at the mid span away from supports. For easy drawing, you may click on snap options so that Etabs accurately shows you a triangle shape for the midpoint. So I can see a triangle shape here. That means it is the midpoint. You may zoom in for more accuracy. Strips should be nearly straight. When your line is slightly green, that means that the line is accurately straight, parallel or perpendicular to the axis directions. Now, middle strip was drawn. We need to go for the dimension line here so that we may draw the remaining strip in the remaining areas. The dimension is 7.9 feet and the strip dimension is approximately 5 feet or 4.999. So the remaining middle strip will come out in the remaining width. 7.9 minus 5 or 4.9994 gives us 2.9173. Multiplied by 12 gives us 35 inches strip width. So now we are done with drawing the strips for layer A of reinforcement. The reinforcement will be parallel to the strips drawn. Now hide the strip layer A so that we may easily draw a strip layer B, which will be perpendicular to the strip layer A. Now the column strip width will remain the same as we have to select the shorter of the both directions. That was 60 inches. Make sure that you select the column strip when drawing column strip and middle strip when drawing middle strip. You need a little bit practice on these steps. Now we need to draw the middle strip so that you can get the reinforcement in the middle strip direction. Usually column strip have negative moment and middle strip have a positive moment dominance. Now you may turn on the strip layer A. Turn off the slabs. Now you need to select the strip column strips in the layer A. Turn off beam and columns for more easy selection. Select the column strips only. Make sure we select the column strip in layer A. Go to design. Actually, go to concrete slab design and go to reset all flexure overrides and strip based design. View revised flexure overrides strip based. Select the proper rebar material you want to assign in the strip. Now select the middle strips in the layer A. Go to design, concrete slab design, view revise design overrides. Select the rebar material and press OK. You need to repeat the similar procedure for the strip layer B. First of all, turn off the strip layer A's visibility and turn on strip layer B visibility. Select the column strips in the strip layer B. Select the rebar material. Click on OK. Now similarly do the same for middle strip. Select the middle strip. View revised preferences. Select the material. Now once we are done with assigning the material or rebar material, you can say, to the strips, we will have to select the whole structure. If it is a multi-story structure, then replicate it to other floors. Select all. Replicate by story. Since we have modeled it in first floor, so copy it to second floor. And since ground floor is a plinth level, it does not have a slab. So turn off the floors and copy the remainder parts to the ground floor, or you can replicate it. You may check the structure in 3D view. Actually turn on the floors so you can see which floor has slab. So now it is clear that we did the correct thing, since ground floor does not require slab as it had slab on grade. Now we need to run the analysis. The deflection limit according to ACI code is shown. We need to use the deflection limit for the slab conservatively for plate slabs and flat slabs. The deflection limit should be less than the limit, that was 1 inches. Select the critical or long-term deflection case. Check the deflection in the most critical regions of the slab. A minimum tolerance should be allowed, or you may revise the cross-section of the slab if the deflection coming out of analysis is greater than the deflection limit, which you can always increase the cross-section or the strength of concrete, which will then reduce the deflection and bring it in the limit. Check the deflection in all the spans, critical regions where you suspect the deflection may be maximum. Or if you don't have any idea where the deflection will be maximum, so click on deform shape and view it in 3D or start animation that time so that you may get a clear idea where the deflection will be maximum due to that combination. The structure was simple here so that I know the deflection will be maximum due to positive moment in the mid spans, as it is uniformly supported from all the directions by beams. So in particular spans, the deflection is higher than 1 inches like this one span. So I may ignore the 0.006 inches exceeding the limit, which is very less. Here the limit was exceeded by 0.15 inches as the limit is 1 inch. You may increase the thickness of the slab here or provide drops. For now, I will ignore this and continue to design the slab. You can also provide a camber here if you don't want to increase concrete strength or slab thickness. Now go to the first floor and design the slab. You can see a pattern of reinforcement in the slab here. The blue color line shows the bar placement. Go to concrete slab and display flexural design. Check the minimum reinforcing criteria so that the minimum reinforcement according to the code you selected will be given to the slab if the moment is very low. Define the bar spacing for uniform mesh which you want in the slab. Since the spacing we selected was high, so now for less conservative design or more economical design, you may increase the spacing so that you may get extra bars here. So the mesh is also over designed here, so we may increase the bars or decrease the bars or increase spacing, or you can say increase the spacing by decreasing the bar density. Sometimes the spacing option freezes. For now I am going for number 4 bar, hoping that I may get extra bar and the slab will be more economical. Still no extra reinforcement, that means the slab is still over designed. The option freezed is corrected by once clicking on none and then again selecting the typical uniform reinforcing option. I placed spacing as 8 inches now, so now we are starting to get the extra reinforcement here. That means the slab is not over designed now and we may place extra reinforcing where it is required, not everywhere. Go to display flexure design, click on layer B. Now checking layer B whether it is designed over or accurate design. You can see the blue color is the bar and the black line when we hover over it shows the reinforcing extent. You may increase the graphic preferences or the font size. So now you see the font size is a bit increased. You may further increase the font size until it becomes visible to you. Press OK. So now it is visible. We need to save it and then go to AutoCAD. We selected number 4 bars, which is nearly conservative. You may decrease the bars to further if you wish to provide extra reinforcement. I have already drawn it in AutoCAD. Now I will copy the reinforcement from Etabs to AutoCAD. The mesh is given on the basis of the bars which we selected for mesh for top and bottom, and the extra reinforcement will become apart from the mesh. Now starting with placing the extra reinforcement in the AutoCAD drawing. Now editing the bars, Since the bars are too less, so that I will remove the center to center spacing and just write the number of bars. We are copying the number of bars from Etabs into AutoCAD. The framing plan was already drawn by my draftsman, which every engineer has been provided with in an office. Or you may follow the channel so that you can learn complete AutoCAD using tools which I will upload further. For the next row of reinforcement, 3 number 4 bars. Actually, it was 2 number 4 bars. Now, most probably here it would be 3 number 4 bars. Since the slab is symmetric, 2 number 4. You may also increase number of bars, like increase it to number 2 number 4 bars conservatively. Now going for the last bars in the layer A, the black line shows the extent of the number of bars while placing them, and the blue lines show the actual bar. The length of the blue bar shows the length of the bar. Actually, it would be similar to the bar when it is placed. 2 number 4 bars. 2 number 4 bars. Delete the unwanted reinforcement which my draftsman placed. The detailing according to ACI code is shown, that is the 1/3 of the span, that is the longer span in both the direction. The top bar shall be at least L by 3 or L by 4 so that adequate development length is provided after reaching the point of contraflexure. The development length is provided so that bar is properly anchored within concrete when cracking occurs. So the extent of this red top bar is at least 1/3 of the span in both directions. The longer span is preferred for the bar length, which was adequately placed by my draftsman. Actually, I mistakenly deleted my reinforcing bar from here. So you may press Ctrl plus Z to undo. In AutoCAD. To learn AutoCAD in detail, you can subscribe to my channel and I will be uploading the AutoCAD tutorials and Revit tutorials on it. If I didn't notice it right now, then I would have to do a number of undos to get to this point. So now we are done here. Mention the level of the slab. It is a good practice and is usually done in framing plans. The thickness of the slab is in inches, that is 10 inch. Now the layer A has already been drafted. So now we will display the design of the slab for layer B. The number of bars required are 535. 5 number 4, 3 number 4, actually it's 3 number 4, 5 number 4, 2 number 4, now we move on to deleting the unwanted bars. So now the grid 4, 4 number 4, 2 number 4 and 4 number 4. Two number 4, and the last was 4 number 4. So the grid number 3, we go to grid number 3 and delete the extra unwanted bar from 2 as well. So there is less room for mistakes. So now grid number 3, we have 4 number 4, 2 number 4 and 4 number 4. 4, number 4. So now the last remaining grid. Five, number 4, 3, number 4, and 5, number 4. 2, number 4. So now we are done with labeling the reinforcement here. You may also check for the bottom reinforcement. It is already imposed as minimum reinforcement, since the moment will be very less in positive direction, so there is no bottom reinforcement. In layer B, display flexure design and check for you can increase the scale factor for reinforcing diagram. Still no bottom reinforcement. So now you can see by increasing the scale factor you can get a larger diagram. You may uncheck the fill diagram option if you want only the numbers to be displayed, which is also an easy way, but I like the graphical way because it gives me an idea that the larger reinforcement will be placed here. Thank you for watching. Please subscribe to the channel for David, AutoCAD and a lot more software tutorials to come.